Now, what's the reality? This is reality. Reality is this. Suppose we consider two things. Suppose we consider a ratio. And this ratio is what we call the length divided by radius of gyration, which is L over R. Just the reason why we do that is just to make that dimensionless. So L is your length and R is radius of gyration. And the other one is what is just stress. They actually follow this kind of relationship. Like this. They actually follow this kind of relationship. Actually, I like to reverse them because if I'm going to draw it vertically, so please, sorry about that. Let's just switch these two, all right? But the curve is still the same because it's log sum of exponential function. Okay, like this. Now, if we look at the value of L over R, when the value of L over R becomes very, very large, what does that mean? That means, suppose you have the same cross-section, right? It's the same cross-section because your R, radius of gyration, depends on only on the cross-sectional property. Has nothing to do with the length. Length is something else. So when the value of L, the ratio between L over R becomes very large, that corresponds to what we call long columns. Because the column is very long, this is L. But you still have the same cross-section. R is still the same. However, if I preserve the same cross-section, but then make this length of the column become very short, that would reduce the value of L over R. Don't you think, right? Therefore, when L over R becomes very small, that corresponds to what we call short columns. So here, in this region, somewhere here, this is what we call long columns. And somewhere here, until 0, this region is what we call short columns. So let me draw it. Here to somewhere here. This is short columns. Okay. So what's this curve? This curve is the buckling curve. Now the buckling curve, of course, when it intersects with the yield stress, and that actually will give us different behavior. So yield stress is supposed to be somewhere here, sigma y. So this is what we have learned. Buckling has something to do with boundary condition and geometry. In this case is the length and cross-sectional property, which is radius of gyration. When the column becomes very, very short, the failure of the columns usually is dominated by yielding, not buckling, which makes sense, right? Think about that, you have very short column and the buckling stress is going to be very, very high, but it's not going to buckle on it, it's going to yield it first. On the other hand, when the columns becomes very long, you will not yield, you will actually buckle first. So this is something that you need to keep in mind, that depending on really what is the type of the column that you're dealing with. For these two, actually they are empirical equations for you to calculate the boundaries or the definitions for the threshold values of L over R to determine whether the columns you're dealing with, whether it's a short column or it's a long column. That's no problem. You have lots of empirical equations to use. If the short column, you already know that for sure, buckling will not dominate the value, it will be yielding. But for long columns, you know that that's buckling is going to dominate. You will not yield, you actually will buckle. Now, that leads us to what? That leads us to the the region in between, right? That is really what your company needs you for. They already have equations for long column and short columns, but when it's an intermediate columns, that's a tricky one. Because for the intermediate columns, the buckling is actually the combination of yielding. The failure of the column is a combination of yielding and buckling. That means in this region, part of the cross-section may yield, but it has not failed yet. The buckling will also occur. Okay, so let me recap first. When I said for long columns and buckling dominates, that means in this region, there won't be any yielding because this stress is way below the yield stress, right? That means for long columns, when the column fails, everything in the cross-section is still within the elastic range. Yet the column fails. For short columns, is the other way around. For short columns, there's no buckling. Everything is going to yield. The failure is dominated by yielding. Now, for intermediate columns, that's in between. You're going to have partial yielding and partial buckling. So that's the tricky one. Which one is what structural engineers really cared about is by recognizing that part of the cross-section will be yielded. We want to know that what is the maximum bearing capacity, which is this curve. We don't, I mean, in principle, we know it's a combine, right? But what we really want to know is what will be the maximum bearing capacity. Because for long columns, you just calculate PCR. For short columns, you just calculate PY. So that's what we do. For here, this region is just PCR. That's all you need. In this region is PY. And what's PY? PY is just A times sigma Y. So that's easy. But for in between, we're not going to use PCR. We're not going to use PY. We're going to use P failure. So this is what we call PF. Because it's not simply just PCR, nor is it just PY. It's a combination of these two. And tonight we will also show you how we can calculate this force. Okay. All right. And let me come back to another example. The next example is, I'm going to finish the next example tonight. So this is going to be example 10, right?
One question, Professor.
Yes.
If you go back to that graph, would the blue line for the yielding stress intersect the curve somewhere in the intermediate column section?
No, this is the failure curve. That means when the loading above this curve, the structure already fails. So for the long columns, the loading will never go up to the yield stress level. It will fail right here. This is where it's going to fail. In this region, well below sigma Y.
But would the yielding stress of this blue line, would that intersect with a curve?
No.
Somewhere
no,
between the...
No, why it wouldn't is because, like I said, as long as you stress above this level, the structure already fails. This region does not exist. That means...
Which region?
Whatever above here, there's no intersection. Yeah. Let me be clear. This is what we call the failure region.
Yeah.
This region is just failure.
Mm-hmm.
That meaning what? Meaning that suppose you have a structure and suppose you start loading it from here all the way. Once you hit this envelope curve, the structure fails.
Yeah.
So you won't be anything going up. Once you hit the envelope or hit the boundary of this region, the structure already fails. And at the point, this corresponding stress level is well below yielding stress. That's what I meant. So there's no intersection.
Yeah, I understand. Yeah, I understand that. Okay.
All right. So let's move on to example 10, right?
I think it's example 8.
Example 8. Yes, example 8, you're right. Somebody is keeping the number for me. I appreciate that. Example 8. So what is this problem? Now in this case, we're going to change the boundary condition. We're going to change to this, to fixed-ended on both ends. So the column looks like this. And the loading applies like this. Like that. And we're going to have also call this one to be A and B, like what we did before. And everything else, of course, remains the same. So you still have L being the total length, and you still have E, and you still have I. When I denote it this way, when I use just a value to describe this column, that means it is a homogeneous column. So they mean differently. When I said there's only one value, E, that means homogeneous. Cross section. When you give you just one value of Y, that means uniform. Cross section. So one is for material, the other for geometry. And the capital L is, as you know, the total length. Our objective is always to find what is the critical load of this problem. So start with the first one. Now we're going to, pretty much you know what I'm going to do, use the force approach. And to do that, you're going to establish the force free body diagram. And if we take this region to look at what is the kinematic description of this deformed column at this end, you will know that with a boundary condition, which is something like this, when the column joins support A, the right angle must be preserved, right? Otherwise, that's not what we call fixed-ended. So that means somewhere here, you have to go like this. And then the cross-section may go something like this, with this angle still to be the right angle. And this is what we call point A. Of course, let's not forget about defining the coordinate system X and Y's. X is always the longitudinal, and Y direction usually will choose the positive direction as a Y direction. So in this case, we're going to call the right hand pointing direction to be the Y direction. That means this is our X, and this is our Y is in pointing to the right. And that means our X is this, and our Y is this. By considering all the forces here,